the product and quotient rules. The product rule states that if f and g are both differentiable functions, then the derivative of the product of f of x times g of x is f of x times the derivative of g of x plus g of x times the derivative of f of x. This notation is a little bit cumbersome, so over here I have a more concise way to remember this formula. So the derivative of f times g is f times g prime plus g times f prime. This is an important result, so let's prove it. So we're going to start with f of x times g of x. The derivative of this, by the definition, is the limit as h goes to 0 of f of x plus h g of x plus h minus f of x g of x divided by h. This is simply applying the definition of a derivative. Now I'm going to rewrite this by stating this is the limit as h goes to 0, f of x plus h times g of x plus h, and I'm going to apply a little bit of a trick here. I'm going to subtract f of x plus h times g of x, and I'm going to add f of x plus h times g of x. And then I have minus f of x g of x all over h. Now, this is 100% legal because all I did was add and subtract the same term, which cancel each other out. Next, what I'm going to do is rewrite this as two fractions. So I have the limit as h goes to 0, f of x plus h times g of x plus h minus f of x plus h times g of x all over h. Plus f of x plus h times g of x minus f of x g of x all over h. And all I'm doing here is rewriting this single fraction as the sum of two fractions, since they have a common denominator. And now, this is the tricky part. I am going to notice that there is an f of x plus h here and an f of x plus h here. I'm going to factor that out. So we get the limit as h goes to 0, f of x plus h, and we're going to multiply that by g of x plus h minus g of x over h, plus, and then I will take this limit and apply it to the second fraction. And here I can see that I have a g of x as a common factor, and I'm going to factor that out. So we get g of x multiplied by f of x plus h minus f of x, all divided by h. Now, since f is a differentiable function and g is also a differentiable function, I'm going to apply this limit to each of these, and then I can evaluate each of those limits very easily. So I have the limit as h goes to 0, f of x plus h, times the limit as h goes to 0 of g of x plus h minus g of x over h, plus, and then I'll do the same thing for the second part. I have the limit as h goes to 0 of g of x multiplied by the limit as h goes to 0, f of x plus h minus f of x over h. Now, because f is a differentiable function, it is also a continuous function. And that means that I can evaluate this limit by simply plugging in h equals 0. So this becomes f of x plus 0 which is basically just f of x. And that's multiplied by this limit. But if you look closely at that limit, this is the definition of the limit of g of x. So that's just g prime of x. Plus, over here I have the limit as h goes to 0 of g of x. G of x is a constant compared to h. So that's just going to equal g of x. And then this limit is also the definition of the derivative, but this time it's the derivative of f of x. And so that's f prime of x. And so in the end here, we have the result. We have the derivative of f of x times g of x is f of x times g prime of x plus g of x times f prime of x. The important thing about the product rule is that you're able to use it reliably. So in the first example, we have a function f of x equals x times e to the x, and we want to find the derivative. So actually, let's start by writing down the function f of x is equal to x times e to the x. And I like to think of this function as being my first function, and the second function here, e to the x, as my second function. And the way the derivative works is we're going to take the first function and we're going to multiply that by the derivative of the second function. And then we're going to add the second function multiplied by the derivative of the first function. I find that it's much easier to remember it in this way than it is to remember it with f of x's and g of x's. So in this particular case, f prime of x is going to be the first function x multiplied by the derivative of the second function, which was e to the x, plus, then it will be the second function e to the x multiplied by the derivative of the first function. And so this is going to be x multiplied by the derivative of e to the x is e to the x, plus, and then we have e to the x multiplied by the derivative of x, which is 1. And this is x e to the x plus e to the x. And if you factor out e to the x, you get e to the x times x plus 1. And this is our first derivative. Now, let's write that up here at the top. So the answer to part A is f prime of x is e to the x times x plus 1, or you could write that as x plus 1 times e to the x. Now for part B, we want to find the nth derivative, which might seem a little strange, but basically that means we want to try to find a formula for the nth derivative. So to do this, what we're going to do is find the next several derivatives and hope to see some kind of a pattern. So let's work on finding the second derivative. So to find our second derivative, we're going to start with our first derivative, which is x plus 1 times e to the x. And to do our second derivative, we are going to use the product rule, because we have the product of x plus 1 multiplied by e to the x. So the product rule states that the derivative is going to be the first function, x plus 1, multiplied by the derivative of the second function, plus, then we're going to take the second function, e to the x, and multiply it by the derivative of the first function. So we're just applying the product rule, but now we're applying it to the first derivative. And so doing the math here, we get x plus 1 times the derivative of e to the x is e to the x, plus e to the x multiplied by the derivative of x plus 1 is 1. So now if I factor out e to the x, what I have left over when I factor that out is x plus 1 plus 1. which of course is x plus 2. So my second derivative I can rewrite as x plus 2 times e to the x. Now, I don't know enough yet to see if I have a pattern, so what I'm going to do is take the third derivative now. So now we're starting with our second derivative, and let's go ahead and start computing our third derivative. So again, to take the third derivative, notice that we have a product between two functions here. So the third derivative is going to be the first function, x plus 2, multiplied by the derivative of the second function, e to the x, plus the second function, e to the x, multiplied by the derivative of the first function, x plus 2. And this is equal to x plus 2 times the derivative of e to the x is e to the x, plus e to the x multiplied by the derivative of x plus 2 is 1 again, right? Because the derivative of x is 1 and the derivative of 2 is 0. And then just like before, if I factor out e to the x, what I have left over is x plus 2 plus 1. And of course, this is e to the x times x plus 3. And so I now know that the third derivative is x plus 3 times e to the x. And so I'm starting to see a pattern develop. The first derivative was x plus 1 times e to the x. The second derivative is x plus 2 times e to the x. And the third derivative is x plus 3 times e to the x. So I'm going to guess that my fourth derivative might be equal to x plus 4 times e to the x. But let's verify it to be sure. So we start with our third derivative. The fourth derivative will be found by using the product rule. We'll take the first function multiplied by the derivative of the second function plus the second function multiplied by the derivative of the first function. This is equal to x plus 3 times e to the x plus e to the x times 1 again. And when we factor out e to the x, we get e to the x times x plus 3 plus 1, which is e to the x times x plus 4. And so indeed, I can confirm that the fourth derivative is x plus 4 times e to the x. So now I'm very confident that we have a pattern. And so what that means is, if true, the fifth derivative would be x plus 5 times e to the x. And the sixth derivative would be x plus 6 times e to the x. So if we continue with this pattern, the nth derivative appears to be x plus n times e to the x. Now, this is a bit of an extreme example for your first example using the product rule, but it's also a good example because each time I took the next derivative, I had to use the product rule again. For our second example, we want to differentiate the function f of t is equal to the square root of t multiplied by a plus b times t. Let's keep in mind that a and b are constants. The variable in this function is t. So if I have f of t equals the square root of t times a plus b times t, I'm going to apply the product rule to get the derivative because I have the product of two functions. Namely, I have the square root of t as my first function and a plus b times t as my second function. So if I use the product rule, the derivative is going to be the first function, square root of t, multiplied by the derivative of the second function, which is the derivative of a plus b times t, plus then we'll take the second function and multiply it by the derivative of the first function. Now, sometimes students can get a little confused with something like this because they see a bunch of letters here. But keep in mind, t is the variable. So when you take the derivative of a is a constant, and the derivative of a constant is 0. And the derivative of a number b times t is just b. And so this becomes the square root of t multiplied by b. Plus, then we have a plus b times t multiplied by the derivative of the square root of t. Now, we talked about how to take this derivative in an earlier lesson. And so I'm just going to remind you that the derivative of radical t is 1 divided by 2 radical t. And so this is equal to b times the square root of t plus a plus b times t divided by 2 times the square root of t. So all I'm doing here is making a fraction out of this and multiplying these together. Now, you could leave your answer like this, but you also could simplify this by getting a common denominator. So my common denominator here would be 2 radical t. So I would have to multiply the top and bottom by 2 radical t here. This would give us 2b, and then radical t times radical t is t, over 2 radical t plus a plus bt over 2 radical t. And now I have a common denominator of 2 radical t, and I have 2b times t plus a plus 1b times t. And I can simplify this into a plus 3bt divided by 2 radical t. Okay, now, again, both of these answers are acceptable, but sometimes this second answer is a little bit better. Now, I want to show you that you could actually find this derivative using a completely different technique. So let's remember that we could use the distributive property here, and we can write radical t times a is a radical t, plus, and then radical t times b times t is the same as bt times radical t. And I can rewrite this as a t to the 1/2 power plus bt to the first power times t to the 1/2 power. And if I combine those powers here by adding, I get bt to the 3/2 power. So I'm just rewriting my original function. And now when I go to take the derivative, I don't have to use the product rule anymore. Because remember, a and b are constants. So when I take the derivative of a times t to the 1/2, I can just apply the power rule here because a is a constant. So the derivative is a times 1/2 t to the negative 1/2 power plus, and then the derivative here works the same way. 3/2 comes down, and I have b times 3/2 t to the 1/2 power. And now if I just simplify this, I have a times 1 over 2 times 1 over t to the 1/2 plus b times 3 over 2 times t to the 1/2. And then we can make a fraction out of each one of these. And if I combine these, I get a over 2 radical t. So keep in mind here, I am rewriting this as the square root of t. Plus, and then I have 3b radical t over 2. Okay, so again, I'm writing this as radical t. And then if I want to combine these together, I would just multiply the top and bottom by radical t, and that would give us a over 2 radical t plus 3bt over 2 radical t. And this is because radical t times radical t is t. And now we have a common denominator of 2 radical t, and the numerator is a plus 3bt. And if you rewind the video, you'll see that this is the same answer that we got from the product rule. Now, I'm not telling you to do it this way or to use the product rule. I'm basically just showing you that sometimes there's more than one way to get the same answer. Let's do a third example of the product rule, which is a little bit more abstract. Here we have a function f of x is equal to e to the x multiplied by some unknown function g of x. And we do know g of 0 is 2 and g prime of 0 is 5. And we want to find f prime of 0. So what's really important is you need to find f prime of x first. You cannot find f prime of 0 straight away. You have to find f prime of x first. So if f of x is e to the x times g of x, to find f prime of x, I'm going to use the product rule for these two functions. And the product rule says you take the first function, e to the x, and you multiply it by the derivative of the second function. Well, the derivative of g of x is g prime of x. Plus, then we're going to take the derivative of e to the x and multiply it by g of x. But the derivative of e to the x is e to the x. So we have e to the x times g prime of x plus e to the x times g of x. And this is the derivative f prime of x. Now, if I want to find f prime of 0, I simply need to let x be equal to 0 everywhere you see an x over here. So we're going to have e to the 0 times g prime of 0 plus e to the 0 times g of 0. Now, e to the 0 we know is 1, and g prime of 0 they told us was equal to 5, plus e to the 0 here again is equal to 1, multiplied by g of 0, which they told us was 2. And so this is simply 5 plus 2, which is 7. So when you get a problem that's a little bit abstract, and they ask you to do something that might seem a little bit unfamiliar, just remember that in order to find a derivative evaluated at any particular number, you need to find the derivative as a function first. And then it's just a matter of plugging in. So next we have the quotient rule. The quotient rule states that if f and g are differentiable functions, then the derivative of f of x divided by g of x is g of x times the derivative of f of x minus f of x times the derivative of g of x, all divided by g of x quantity squared. And here I have a shorter version of that. The derivative of f over g is g times f prime minus f times g prime divided by g squared. Now, again, I don't really care much for the f and the g notation. So the way I like to think about the quotient rule is I like to think that I have a top function and a bottom function. And when I go to take the derivative, this formula says I take the bottom function and I multiply it by the derivative of the top function minus, then I take the top function and I multiply it by the derivative of the bottom function, and then I divide that by the bottom function squared. I think when you say it like this, it stays with you longer than if you say it with f and g. But how you remember it is completely up to you. Let's go ahead and take a look at an example. I'm not going to prove this rule. The proof is very similar to the proof for the product rule. So in our example here, we have a function y equals x squared plus x minus 2 all over x cubed plus 6. And I want to find dy dx, the derivative. So the rule says when you have a quotient of two functions, this is the top function and this is the bottom function, the derivative is the bottom function multiplied by the derivative of the top function minus the top function multiplied by the derivative of the bottom function, all divided by the bottom function squared. So the most important aspect is that you just get these functions and their derivatives in the right place. And it's very important you don't get these two backwards, because when you're subtracting, the order matters. So we have to start with the bottom times the derivative of the top and make sure that we don't get that backwards. Okay, now let's go ahead and take these derivatives. So we have x cubed plus 6 multiplied by the derivative of x squared plus x minus 2 is 2x plus 1. Then we have minus x squared plus x minus 2 multiplied by the derivative of x cubed plus 6 is 3x squared. And then don't forget the bottom. So we're going to divide by the bottom function quantity squared. Now it's just a matter of simplifying. So to simplify this, I am going to multiply out the top very carefully. So this gives us 2x to the 4th power plus x to the 3rd power plus 12x plus 6. And then right here you have to be extra careful because we are distributing 3x squared times all of these, but we also have a negative. And actually to do this, I find that it's kind of helpful to rewrite this in this way. So what I'm doing is taking the 3x squared and I'm putting it right here. And then I'm just going to distribute negative 3x squared to each of those terms. Okay, so when we do that, we are going to get negative 3x to the 4th minus 3x cubed and then plus 6x squared. And then all divided by x cubed plus 6 squared. Now we'll just combine like terms, and so we have 2x to the 4th, take away 3x to the 4th. That gives us negative x to the 4th. And then we have positive 1x cubed and negative 3x cubed, which is negative 2x cubed. And then we have plus 6x squared plus 12x plus 6. All divided by x cubed plus 6 squared. And in this case, I'm going to stop here because even though that numerator might be factorable, it's going to be a lot of work to factor this. And so in this case, I'm just going to leave the answer as is. In our next example, it is actually very similar to the third example that we did. So here it says, if h of 2 is equal to 4, and h prime of 2 is equal to negative 3, find the derivative of h of x over x evaluated at x equals 2. So a big thing here is just understanding the notation of what they're asking you to do. So they're asking us to take the derivative of this function and then plug in the number x equals 2. So let's not worry about plugging in x equals 2. Let's just focus on taking the derivative of the function h of x over x. And this derivative, of course, will be found by using the quotient rule. So again, the quotient rule states to take a derivative of a fraction, you will take the bottom and multiply it by the derivative of the top. So the bottom function is x, and the derivative of the top is h prime of x. Minus, then we'll take the top function, which is h of x, multiplied by the derivative of the bottom function. So that's the derivative of x. And then divided by the bottom function squared. And so the derivative with respect to x of h of x over x, if I just simplify a little bit, I'm going to clean this up by saying this is equal to x h prime of x minus h of x times the derivative of x, which we know is 1, and then divided by x squared. So this is the derivative of that function. Now, the second part of this is we're going to plug in x equals 2. So the derivative with respect to x of h of x over x evaluated at x equals 2 means we're just going to plug 2 everywhere you see an x here. So that's going to give us 2 times h prime of 2 minus h of 2 divided by 2 squared. Now in the beginning, they told us h prime of 2 is negative 3 and h of 2 is positive 4. So I'm just going to plug those values in down here. So I have 2 times h prime of 2, which is negative 3, minus h of 2, which is 4, divided by, and then in the bottom we have 2 squared, which is 4. So this is negative 6 minus 4 divided by 4, which is negative 10 divided by 4, which simplifies to negative 5 over 2. In our final example, we want to find the equation of the tangent line to the given curve at the specified point. So our function is 1 plus x over 1 plus e to the x, and the point of tangency is x equals 0, y equals 1/2. So first we need the derivative, so dy dx is going to be found by using the quotient rule, which says we take the bottom function and multiply it by the derivative of the top, minus, then we take the top function and we multiply it by the derivative of the bottom, and then divided by the bottom function squared. So now let's go ahead and do the math here. We have 1 plus e to the x multiplied by the derivative of 1 plus x, which is just 1, minus 1 plus x times the derivative of 1 plus e to the x, which is just e to the x, divided by bottom function squared. Let's do the math here. We have 1 plus e to the x times 1, which is 1 plus e to the x. And then here we have minus 1 times e to the x, which is minus e to the x. And we have minus x times e to the x, all over 1 plus e to the x squared. And then the e to the x's cancel out, and our dy dx is 1 minus x e to the x over 1 plus e to the x to the second power. So again, this is dy dx. Now from this, we need the slope of our tangent line. The slope of your tangent line is dy dx evaluated when x is equal to the x coordinate of the point of tangency, which is 0. And this is going to be 1 minus 0 times e to the 0 divided by 1 plus e to the 0 squared. And this is 1 on top, and then e to the 0 is 1, so we have 1 plus 1 squared, and when you do the math on that, you get 1/4. So the slope of our tangent line is 1/4. The point of tangency is the point 0, 1/2. And so now if we apply this using the equation of a line and we solve for y, we should end up getting y equals 1/4 x plus 1/2. And this concludes this lesson.